For section 3, we're going to be looking at the antiderivatives of formulas, and we're going to find all the different ways that we can integrate or undo our derivatives in a very systematic sense and find the rules for that. Before we can go into that, we need to first review our derivative rules so we know how to undo them. And so let's just kind of go over those here. And so we've got first the constant multiple rule. And the constant multiple rule says that if you have a coefficient in front of your function like this k, that it's just going to go along for the ride. It's not going to change how you take the derivative of it. It just goes along for the ride, possibly gets multiplied in. The sum and difference rule says if you have basically multiple terms or different functions being added together, that you just take the derivative of them and add them together. The same is with your subtraction. The power rule says that if you have a power, remember this one, you bring it out front, subtract 1 from it, and that creates your derivative. There are some special cases with that one. The derivative of a constant is just 0. The derivative of x is just 1. Very special cases there. Exponential functions, the derivative of e to the x is just e to the x. More specifically, if it were, say, e to the u or u is some function, its derivative would be e to the u times u prime. Just rewrite your e function, put the derivative of the exponent out next to it. The derivative of a to the x is you rewrite your a to the x times ln a. More specific, if it was a to the u, then always write my a to the u, ln of a out front, derivative of the exponent. The derivative of your natural log is 1 over x, or more specifically, we use this one a lot, and you saw it on your last exam possibly, is you just write the fraction as whatever you're natural logging on bottom and its derivative on top. If you need any review of these derivatives or help with it, please seek me out through Canvas messaging or office hours. I'll be happy to help you build a better foundation of those derivatives so that as you're moving through chapter 3, you can better execute the antiderivatives. And so in this chapter, that's what we're going to be looking at. So now I'm going to take each of those individual rules and work them backwards. And so f and g are our functions of x, k, n, and c are all constants. And so let's look at this. So the constant multiple rule, you can see that if I have some kind of coefficient there, we can bring it out in front of that integral sign. And so again, it just goes along for the ride. That's really nice because sometimes that can simplify up what you're working with in order to help you to maybe see a simpler function going on. If you are adding or subtracting two functions in integrals, you can separate them, and that's going to come in handy as we work some concepts later on this chapter. Now here's probably the main one that you use, just like with derivatives. You saw that when we were taking the derivative of some x to n, that we bring it out front and subtract 1 from it. So if I'm trying to do the reverse and take it back to the original function, then I'm going to go to now add 1 to that exponent and divide by the new exponent so that we cancel out what's going on here in the front. So you can see it more clearly written that if you have some x to the n, you're going to be adding to the exponent and dividing by the new exponent. But again, this is the reverse of what we did with derivative. Derivative, we brought the exponent out front, subtracted 1 from it. So you can see instead of subtracting, we're adding. Instead of multiplying, we're dividing. Special case, if you just have some number here, such as say the integral of 3 dx, you're just going to put an x on it. And then of course, don't forget all of your plus c's throughout these functions. You always need that plus c on there. That will just be a -1 as you're working through your exams. If you forget that chart, I like to call him Charlie, that little constant of integration. Your exponential functions, you can imagine, again, we're just reversing everything. Well, e to the x, it follows suits that its derivative is itself, so its integration is itself. A to the x, instead of multiplying by ln over a, we're going to be dividing by ln of a, just reversing everything. And then if you see this integral of 1 over x, that's just ln absolute value of x. Now we always put these absolute value of x's because if you go back to your basics of when you started with working with natural logs, possibly in an algebra course, etc., the domain had to be restricted because there was issues when we worked with certain areas of that domain. So that's why you're going to see that absolute value there as well. But again, don't forget plus c on all of these values. Now I'm going to go ahead and erase these. Let me erase everything we just wrote. So that right there will be a really good screenshot for you or picture of, okay, here are the basics of my integration, and now we're going to work through these. So let's look at this first couple of examples. So example 1, find the antiderivative of 3x to the 7th minus 15 square root of x plus 14x squared. So just like when you were doing the derivative, sometimes you need to do some algebra before you do your calculus. So essentially how this would be written, if it was an integral, it might have an integral sign here and then a dx. And I'm going to go ahead and write it like that just for habit and show you how the notation works. So the first thing I want to do is I want to use some algebra and rewrite this so I can better execute those rules that we just talked about. So I'm going to take that square root and I'm going to write it to the 1/2 power. And then I'm going to also bump this exponent up into the top and make it negative. Doing both of these is going to make my life easier because we're going to be applying the power rule. Now our power rule states that what we want to do is add 1 to the exponent and divide by the new exponent. So I'm going to do that here. Now 3 is going to go along for the ride. I'm going to add 1 to the exponent and divide by the new exponent to give me x to the 8th over 8. Minus 15x to, be careful with your fractions and negatives. 1/2 plus 1 is 3/2 divided by 3/2, and we'll address that in just a minute, plus 14x to the negative 1 divided by negative 1 plus c. So now I'm going to clean this up. This gives me 3/8 x to the 8th. 15 divided by 3/2. Let's come over to the side and do a little bit of math here. 15 divided by 3/2. You want to keep it, change it to multiplication, and flip that fraction. So keep it, change it, flip it, or multiply by the reciprocal. So multiplying across, that would give you 30 over 3, which reduces to 10. So it would be minus 10 x to the 3/2 minus 14 over, I'm going to go ahead and put this underneath x plus c. And so that would be the antiderivative of the original function. Now the good thing about this function is it exposed us to 3 different areas that we're going to face with that power rule. It had the fraction, it had just the basic adding 1 dividing by the new number like in the 7. It also had the negative. Use your calculator as you go. Make sure you're getting those coefficients correctly. Just messing up that 15 divided by 3/2 can mess up the rest of your problem. I just want to do a lot of examples with you. So let's do the next example. It says the integral of e to the x plus 12 minus 16 over x dx. And let me point out right here, when I switch from the red to the blue, you'll notice that the integrand and the dx stay together. Once I remove them, plus c came into view. And this would be the work that I would expect to see. I do not want chicken scratch of work on your exams. That is like the very few amount of works that you send me. Homework I get, but exam I need it to be very detail oriented. Notation is on point. Marks will be taking for any missing notation. So whatever we're doing here in the lecture, you need to be replicating in assignments that you turn into me. So let's look at this next one. In this next one, again, I'm going to do a little bit of algebra. I could go ahead and move this x up to the top, but I already know what's kind of going to happen with that. So we can actually just go ahead and integrate. So e to the x, its antiderivative is just e to the x. Whenever you have a 12, you're just going to put an x on it. So any just number, you attach the x. Minus 16 is your kind of constant or coefficient. And then what would be left is, this is like 16 times 1 over x. And we know that the integral of 1 over x dx is equal to ln x. And so this would be ln, absolute value of x, plus c. Now, don't forget, you have to have these absolute value bars. The online homework is going to kind of mark you if you do not. And so that would be my answer. So even though that one did look complicated with the different features that were going on, knowing some of your basics such as e to the x dx is equal to e to the x, 1 over x is ln x, and just recognizing that the integral of 12 is just, or let me write that more generically, the integral of some constant dx is just attach your variable. So that'll help us with example 2. Now let's look at this next example and see what it has us do. It says find f of x so that f prime of x is e to the x. and f of 0 equals 10. Now this is an example of a problem that we're not just going to be looking for, oh, let's find the antiderivative, but we're also going to find the big Charlie, that constant of integration. We're actually going to figure it out for this specific problem. You know, we looked at problems in previous lectures and we said, oh, if we have 2x, that antiderivative would be x squared. And we would say, if we just wanted an antiderivative, you know, we did this example. If we wanted the antiderivative, we said plus c because we didn't know this. This is an example of how we're able to actually find this constant of integration. So first, if f prime of x is equal to e to the x, then the antiderivative would just be e to the x plus c. But since they gave us this little bit of information here, we're going to be able to solve for this c. So remember, if f of x is now f of 0, then we're replacing x with 0. So I'm going to come over here. I'm going to take that antiderivative. And instead of 0x, I'm going to put 0. So that would be e to the 0 plus c is equal to 10. So 10 would be the y value. Now I'm going to solve that out. E to the 0 is just 1. And then subtract that 1 to solve for c gives me 9 equal to c. So I'll say f of x is equal to e to the x plus 9. And so this would be a specific problem that we can actually solve for that c. And so make sure you use all information that's given and complete the problem out from there. In our previous lectures, we looked at a definite integral from a to b, and we really only worked with the setup of it. And we said, okay, this is how we set it up, and we really just worked with that f of x function. Here, I want to put together finding that antiderivative and solving from a to b. So this was just a reminder of the fundamental theorem of calculus, this nice yellow box. And the way we're going to do this is, if we take this integral and we find its antiderivative, which would be capital F of x, notationally we say it's from a to b, and then in our next step we find f of b and then subtract off f of a. I want to show you this in-between step right here so that you can see the notation that's going to follow suit. Once you find this antiderivative and you're going from a to b, go ahead and complete this with a straight up and down vertical line from a to b to remind you you're doing definite integrals, and then plug in your values from there. You want to make sure, again, that all your details are there, your notation is there as you're working through these problems. So, find the area between the graph and the horizontal axis for x between 1 and 2. So we're going to go back to what we were doing in previous sections and do our setup. So we're going from 1 to 2. We're bounded by the horizontal axis, so we're just going to put 3x squared here, dx. Now the first step, and this is what we have not done, we've only done the setup in previous sections, is we're going to find this antiderivative. So I'm going to add 1 to the exponent and divide by the new exponent, and we're integrating from 1 to 2, so new notation here. Clean this up, this gives me x cubed integrated from 1 to 2, and then actually plug it in. 2 cubed minus 1 cubed, that gives me 8 minus 1 to give me 7. And so now we're able to complete that process that we were looking at in other sections where we were able to do the setup of a definite integral, but now we're going to put that together and remember how we work through those. Let's look at this next one. A robot has been programmed so that when it starts to move, its velocity after t seconds will be 3t squared feet per second. Part A, how far will the robot travel during its first 4 seconds of movement? If you, again, reverting back to previous sections, we had time and velocity. And so at the first 4 seconds, this was the area underneath this curve was the distance that we were traveling. So part A, let's set it up. So from 0 to 4, we're going to integrate 3t squared dt. So I'm going to add 1 to the exponent, divide by the new exponent, integrate from 0 to 4. So it gives me t cubed, integrate from 0 to 4. So it gives me 4 cubed minus 0 cubed. And so that gives me a value of 4 cubed which is 64 feet. But again, it's all about that setup. If you need to go back to previous discussions of time and velocity and how to find the distance, then revert back to those lectures. Part B says, how far will the robot travel during its next 4 seconds? Well, that means from 4 to 8, because that would be another 4 seconds of 3t squared dt. Now, we already know that that gives us t cubed. I'm going to integrate from 4 to 8. So I'm going to say 8 cubed minus 4 cubed. Working with my arithmetic there, I get 512 minus 64, or 448 feet. And again, this would be like extending this graph out and finding the next 4 seconds to find our distance. And so again, this goes back to previous discussions, but it's still integrating from A to B. Let's do another one, kind of a different situation. It says, suppose that t minutes after putting 1,000 bacteria on a Petri plate, the rate of growth of the population is 6t bacteria per minute. So again, you've got your time and you've got your bacteria per minute. How many new bacteria are added to the population during the first 7 minutes? And so here's, for instance, 7. And so we're wanting to find this area under the curve to find the bacteria. So I'm going to integrate from 0 to 7 of 6t dt. So first I'm going to find that antiderivative. So I'm going to add 1 to the exponent, divide by the new exponent from 0 to 7. And I'm going to simplify that up. 3t squared from 0 to 7. Then I'm going to evaluate. So 3 times 7 squared minus 3 times 0 squared. And that gives me a value of 3 times 49, or 147. Again, the red part is just what we've been doing with integrals, putting it with definites, but we were able to define that by the information that was given. Now in part B, it says, what is the total population after 7 minutes? Well, the 147 is the new growth. We were putting in 1,000 bacteria. So if we take the 1,000 bacteria that we start with, plus the 147th of new growth, we get a value of 1,147 bacteria. So this didn't go back to a calculus concept. This went back to just information that was given in the problem. So, you know, we've looked at a robot, we've looked at the bacteria. Let's go into the business part of it now. A company describes the marginal cost for production in dollars per item is marginal cost is equal to this function when producing X thousand items. Find the cost of increasing production from 4,000 to 5,000. So we are going to take our marginal cost, because marginal always signify that we need to take the derivative. So I am going to integrate my marginal cost function, 4 over the square root of x plus c dx, and I'm going to integrate it from 4 to 5, because it told me x was in 1,000 items, and so I'm only going to use the 4 and 5. I'm not going to do it out with 3 zeros behind it. So first, let's do some algebra. So I'm going to carry along everything I'm not using so far. I'm going to say this is 4x to the negative 1/2. This would be x to the 1/2. Bumping it up makes it negative. And doing that algebra to get us going gives us a way to apply our power rule antiderivative. So this would be add 1 to negative 1/2 to give us positive 1/2, divide by the 1/2, plus 2x, integrate it from 4 to 5. Let's clean that up. 4 divided by 1/2 gives us 8x to the 1/2 plus 2x, integrate it from 4 to 5. And so that would be 8 square roots of x plus 2x, 5 to 4, and then evaluate. So 8 square roots of 5 plus 2 times 5 minus the whole grouping of 8 square root of 4 plus 2 times 4. So clean that up. I would always write out, especially with this odd evaluation here, I would go ahead and write it all out and then use your probably on-screen calculator to help you with this. And this is going to give you approximately, let's round it, 3.889. And so it will cost $3,889,000 to increase production from 4,000 items to 5,000 items. And these are the type of problems that we're trying to get to or learn enough concepts to be able to work with. Now for the next part, what we're looking at here is just multiple exercises that the book has given us, and I'm just going to kind of sample through some of these. I will not work all 10 of them, but if you see one you would like to be worked additionally, just reach out and let me know. Let's kind of go through and do some quick ones before we get going. And so number 3, you can see it's just a constant dy, so this would just be 12.3y plus c. We can see that number 5 is just an e to the p, so its antiderivative is just e to the p plus c. Number 7, there's another one-year basics, that would be ln x plus c. And so those are the ones that are really quick. Number 4 we include as well. Although pi is written as a Greek letter here, it is still just a value, and so it would be pi squared w plus c. And I know what letter I want to pick based off this dw right here. That's how you know which letter you're going to be using. Make sure you're using the right variables as you go. And again, I'm not going to do all of these. You can see that number 6 is very similar to one that we've done in the lecture. 1 and 2 kind of just follow suit, but let me go ahead and work with them. Number 1, the integral of x cubed, minus 14x plus 5 dx. And so we're just going to add 1 to the exponent and divide by the new exponent as we go. So x to the 4th divided by 4 minus 14x squared over 2 plus 5x plus c, and always reduce down to lowest terms. So I got 1/4 x to the 4th minus 7x squared plus 5x plus c. If you don't reduce, you will see minus 1 did not simplify as you go through these, especially in an exam situation. Let me look at number 9 here. So we got number 1 there. Let's look at number 9. Number 9, we're going to have to do some algebra before we get going. Right now, our skill set doesn't allow us to work with this x minus 2. So I'm going to do my algebra and I'm going to FOIL it out. That gives me x squared minus 4x plus 4 dx. Then we're back to what we did in number 1. So I have 1/3 x cubed minus 4x squared over 2 plus 4x plus c, and then clean it up. So 1/3 x cubed minus 2x squared plus 4x plus c. And so again, number 2 is going to follow suit. You're just working with decimals. Number 6 is similar to the lecture one that we did. Number 8, the algebra you want to do ahead of time is move that up and make it negative. Go ahead and integrate it. Be careful with adding 1, dividing by the new exponent as you go. And then clean that back up to make sure that you did not leave your answers with any negatives. Number 10, last one we'll do, is kind of interesting in the fact of applying your algebra here. You're just going to divide each of these by t to give you t to the 4th minus t dt. And then we can add 1 to the exponent and divide by the new exponent as we go. So don't forget all of your algebra skills as you're working through these, because they will make your life a little bit easier, especially in regards to finding the antiderivatives.